and welcome to this demonstration in which we are going to discuss how to prepare slope and aspect maps. If you recall our discussion which in the 3 previous lectures we have discussed in detail about different methods of slope and aspect and all intricacies, especially about the jet factor and other things. So all these we will see when we do we see the demonstration on a computer or through a GIS software. Another important thing is that here I am going to take deliberately a digital elevation model which belongs to a part of Himalaya, which is a highly rugged terrain, so that we can really see the conditions about slope and aspect and other associated intricacies, especially about jet factor. So let's start with demonstration. So here what I am going to do is let me first add a digital elevation model, and I am going to add a digital elevation model which is a Ester GDM of 30 meter spatial resolution, as also mentioned, part of Himalaya, so that we can see these things. This is what the digital elevation model which I am going to add in our this I have just done. The 1 degree tile I have downloaded from Earth Explorer or similar. There are various such sites from where you can download for your area of interest. Now what we are going to do, we will perform slope. First we will perform the slope calculations or prepare a slope map using this digital elevation model. So for which as you know that there are 2 ways to do it. Either we the one which I prefer is always to go for the this search, and through that I can find very easily the tool which I am looking here. So the toolbox is already there, but instead of toolbox we can use the search method, which I find very easy. We don't have to remember where exactly that tool is residing in the toolbox. So if I just type slope, and then I get the different at different places the slope, how to create slope. I will use the slope which is a part of spatial analyst extension. So this tool I find is most appropriate, and the same way I can also do it on this toolbar, but that is a different story. And now what I will do, we will add this this digital elevation model which is being displayed here as our input raster, and then we will choose either one out of 2 methods, either that is a planar or geodesic. Of course, you have to provide where it would reside the results. So if I accept this one as whatever is the default folder, and output is going to be in degrees, and this method planar. So first we will do with the planar method, and if by mistake if you do not change these values about jet factor, then you would you may get some results. So what deliberately what I am going to do, I am because it is not happy, so what I am going to do, I will just use the default value deliberately, and will prepare a map which is in degree, slope map which is in degree, method is a planar, and jet factor is 1. And let's see what kind of output it creates. Meantime, what I can do, I can start feeding for the next one also. So that will come, let it keep processing. I will use this one again, and will keep as a separate here. So here what I will do, I will rename the file, and because this time I am going to provide the jet factor for this part of the word. So that is 50.5089. So I'm just for simplicity, I'm keeping here 89, and jet factor, of course, I will type as this value 5089. This we have of course calculated with the location, and so jet factor, as you know, we are converting basically our height, that is the jet value, into meters. Height are in meters, so we are converting meters into degree decimal as our xy coordinate. So that is why this jet factor is being used. And then so what we are going to have, the first map which we have just created, which is also being displayed. I will show you soon. Now it is here, and that one is when jet factor is 1. Now here everything remains same except the jet factor is the one which should have been. So let me now process this one also. So we will have, that means, two slope maps top of each other, with one the slope underscore TIF 1 is for jet factor 1, and slope underscore TIF 89 would be for the jet factor 0.5089. Now these two maps have been generated here. Now let's investigate, or here explore what are the changes it has brought while using two different jet factors. So what I will do, I will say I will, this is a Terry reservoir area. So what I will do, I will take this identify tool, and let's see with very high slope values what happens in these two. So what we will choose to with all visible layers, and once I press again, as you can see that the TIF 1, that is the jet factor 1 slope map, is giving for that particular cell, giving value 39.54 degree, and whereas this with jet factor 89, it is giving value 39.20. That means for this particular location, for this particular cell, our if I keep jet factor 1, then it is overestimating our slope. Let's try with some low values like these grain areas, mid grain areas like this. So here this with jet factor 0.5089, and the slope value is 19.927378, whereas in when jet factor equal to 1, it is 20. So again here it is also this jet, when we keep jet factor 1, which is not correct in this case, because latitude and longitudes are in degree decimal, and whereas the third axis, that is z axis or vertical resolution, here is in meters. So these two values are different, whereas in theory we have discussed that jet factor will allow us to convert one to another. So what we are doing, we are converting this height values, that is in meters, to DD by bringing this jet factor. So in that way, again, what we see, let's see some other part. If I do it within the reservoir, let's see what happens, what value we get. Of course, it should come 0, because water body is flat from top, and that is why in both these it is coming 0. There are other green areas also. So if I go in that area and do it, let's see what happens to these very dark green areas like here. Still there are, not like water body, still there are slope, very gentle slopes. So when jet factor is 1, it is coming 3.949, and when jet factor is 0.5 times 0.89, then it is 3.90. So again, what we are observing, that if we keep jet factor by mistake 1, if our x, y and z units are not same and we keep jet factor 1, then it is going to overestimate our slope values. So it is always good, always desirable that we must take care about these x, y and z scale, that these should be equal. If they are not equal, then we should use the jet factor and convert. It is rather easy to convert our meters into DD, which I have done in this demonstration. And if you recall that what we have used the same planar method, except for jet factor, rest of the things remain same. Now I am going to generate another 2 maps with the one with the planar and with the jet factor 1 and with the geodesic and the jet factor 0.5089. So let's do it. I will keep here, will give some name. So for geodesic, I give the name geo and 1, which indicates that jet factor I am going to keep 1, and here geodesic. And once I choose geodesic, you don't have to bother about jet factors. Now it is asking the Z units are in meters. So if they are not in meters, then we have to be very, very careful about this. So while doing this exercise, you have to be little careful about the units again. For time being, because I have said I will keep Z factor 1 and see what happens to our output. And then we will try to compare this one with the one which is we use the option or the method we use the planar method with same jet factor. All 3 we will rather compare all 3 to see what are the changes and then find the differences also. Generally, if you see visually, you may not find much differences. But if we do it with the zoom part and for individual cell, then we start getting these things. So again, we will remain in this area. I am going to choose again, and all 3 surfaces which or 3 slope maps created with 3 different methods are here. And this the top one is showing this is with the geodesic method and jet factor is 1, where this value is 53.137, and whereas when we keep the correct jet factor, that is 0.5 times 0.89, it is giving 52.98, and while jet factor 1 planar method, we are getting 53.32. So in this particular, for this particular cell, there's a geodesic method, and because both are having jet factor 1, so both are giving quite close results, whether it is geodesic method or planar method. Now let me choose another area which is not a very highly sloped area. Here now you would see a large difference that this geodesic method with jet factor 1 is 4.46, whereas the correct jet factor giving you 4.2, and whereas this jet factor 1 planar method is giving 4.26. So that means that geodesic with jet factor 1 is really overestimating the slopes. So whenever you perform any such analysis, whether you are using slope tool or any other tool, the best way, if you are having some ground information, prior information about certain locations of the slope conditions, you can always check, verify or we also say in the remote sensing domain as ground truthing. So you can do the ground truthing if you are having that data available to you. If it is not, then later on also on the field it can be verified whether it is calculating true or not. One way, as I have told you, if you know any high angle slopes already, you can test, or like I know here this is the flat terrain, means it's a water body, and my two slope maps with planar methods having different jet factors are giving value 0, whereas with geodesic and jet factor 1 is giving 0.00983. So that means this one is not giving, for this particular cell, it is not giving accurate value. Now let me try in some other parts which is not the part of reservoir but part of the river. Again, in our two planar methods with the two different jet factors, they are a value 0, but here with geodesic jet factor 1, we are getting some value. So that means that geodesic with jet factor 1 is really giving us very relatively wrong values, because instead of keeping jet factor 1, if we choose the correct units, that means if we make xy and z unit equal, then hopefully we should be getting more accurate results. So it is always true, as I have also told several times, that in GIS after each and every step one should check for errors. And if you are satisfied with the results, then you should go ahead. Otherwise, you recheck, is there something wrong, whether it is with the scales, units, jet factor, and so on and so forth. With this, you will be able to produce most reliable results. Otherwise, and one should know all the details that what it has followed while this calculating such surfaces like slope map in this example. Now what I am going to do next is I will go for the aspect. So again we take the same digital elevation model, which is the Aster GDM 30 meter, and we'll try to calculate instead of slope, here we will calculate aspect, and let's see what happens with what are the options available and so on. Again, I will choose aspect spatial analyst extension tool, and same way you have to provide the file. So this is my input digital elevation model, and here what I will do, I will use word for planar, I will say 1p, or 1 I can remove here, just keep say underscore p, and here no other options are available, so we need not to bother at this time, and let's go and do it. Now output is going to be a floating point, not integer. So we will see that how two different methods bring that, whether they brings the different results or not. So it has created a slope aspect map with the planar method. I will do it with another method, and then we will compare and see that what these two are bringing differences. What are the differences in values, which we can inspect by using this eye tool. Okay, so this one, and here what I will do, I will geodesic, so I will use G word for geodesic, and instead of planar we will choose geodesic method. One other thing we will be doing with the slope map, that we will try to create a difference map, and we'll see that where the more differences are there and where the less differences in slope maps are there. And that way you can create a separate layer which would be the difference of two methods. So that will give you the exact this thing. Now here it has now created two aspect maps which you can see very clearly, that the top one which we are seeing currently is based on geodesic method, and this one is on the planar method. Now if I zoom it in certain part, again I will try to zoom the same part as that part of our reservoir, that is Terry reservoir, and do it with this tool, identify tool. So if I click on a red area, both are giving the values, though the geodesic method is again giving 5.4460, whereas this planar method is giving 5.389, but these are the direction. So the range, they are all falling in this range, that is the north facing slope. And if I go for this one, the pink color one, like here, then these values are very high. Again, this here in this particular case, geodesic is giving less value as compared to the planar. Whether it is true in all other cases, that we can also check it. Yeah. So it is the planar is giving more value than geodesic. So likewise, you can inspect. If you are having ground information, you can verify. Otherwise, if it is possible, it can be checked in the field, and then you can accept the product. Plus also, this part, this we have also discussed, that when values are less than 1 or minus 1 value is assigned, as you can see here, that for the reservoir part, any method, whether it's a geodesic or planar method, both are giving minus values. So that means that this is the flat part, because water body, the top of that is the flat part. And this continues to quite a large extent. But later on, things may not be that visible because the river thickness reduces, but the reservoir is, the dam is here. So these two rivers, one is coming the Bhagirathi and this one is the Vilangana, which if they are coming, and then there is a downstream. So if you click any part of this reservoir body, you would get a -1 value that indicates the flat, because top of water surface is flat. Now I would, what I am going to create a difference map between two sloping surface. So here we can use calculator, and calculator of raster calculator we will choose of, again, spatial analyst extension. Here, since we are having 3 slope maps, so what I am going to do, I will use this one, the one which was giving the jet factor 1 and planar 1. So I will use that one because that was giving higher values, and then the geodesic one. So I will use the planar one, which is this one with jet factor 1, and say this minus then the slope map with jet factor 0.5 times 0.89, and let it save in our this default database and go for results. Still calculating, but soon it will add. Yes. So now this is the difference map. And so we will inspect this difference map along with the two inputs which we have used to create this difference map. So if I zoom on white parts, and then I should be getting a high difference. And what we did, we subtracted this TIFF1 file, slope underscore TIFF1 file minus slope underscore TIFF 89. 89 stands for with the correct Z factor instead of one Z factor. So the difference, of course, in the positive, and this is what you are getting. Another important thing which you can notice here, that there are no values which are less than 0 or less than 1 or anything. That means that if I choose Z factor 1, which is incorrect, I am going to overestimate slope values. If I choose Z factor 8, 9, whether it is a planar method or any other method, then I get more accurate values. So it basically convinces us that Z factor, the care should be taken about the Z factor, that is the XY scale should be equal to Y scale, Z scale, and this can be managed with the Z factor. So we tried on a very wide areas. Let's try on some dark areas where values might be very low. Here values are very low, input values are also given, and then you see that no negative values are there. Of course, say if I go for water body part, all three, since inputs are 0, so the difference will be also 0. So by which basically one has to evolve its own method of checking things. Apart from what we can discuss here or discuss in the literature, one has to, depending on what tool he or she is using, and should devise his own methods to check for errors. So this difference method is another very good method. Plus looking the minimum value and maximum value will give you an idea that what is really happening with your data set. And sometimes you can create some nice products, more nice means here more accurate products, then it is may not be possible. Image differencing techniques which or ratio techniques are very popular in digital image processing of satellite data. But the similar concept, because this is also raster, so similar concept can also be employed. Instead of creating a new product, we are creating a product to check for the differences between two methods, and by which you can very judiciously evaluate that which method is more appropriate for that particular site or that of area of interest. So tools are available. We have to evolve our own way, take care about the scales, units, Z factor, and hope you would get very good results. Very good means here reliable results which you can present with high level of confidence. So with this, I end this demonstration. Thank you very much.